My name is Jaehyeong Sim. I'm assistant professor of Ewha University. Thank you for the introduction. Today I'm going to talk about AutoML for future self-evolving intelligence and hardware. Basically, what we did is designing an AutoML framework to co-design hardware and software. So in the first part of the research, we proposed template-based neural architecture accelerator search. So what we did is we designed neural networks and its corresponding accelerators at the same time, and such that they are optimized for each other. And second part of the talk, we are going to introduce fully automated accelerator design framework. Given neural network as an input, we successfully generate an optimal accelerator as an output. So let me give you a brief introduction about AutoML. So AutoML is short for automated machine learning, which aims to automate the end-to-end process of applying machine learning to real-world problems. So we automate everything related to machine learning, like building machine learning models or deploying these machine learning models, etc. But it comes with several challenges, including increasing computational complexity of advanced models. We have such increasing skyrocketing size of models, such as we have large language models and foundational model. This kind of model, to automate the design process of this kind of model is gonna require a huge amount of computational resources. And secondly, typical AutoML is targeted for improving the accuracy or performance of a single model. But we think that the AutoML should be aware of hardware, meaning that the searched architectures should be optimized for certain target hardware. There remains a challenge regarding this one. So our focus was about reversing AutoML approach to co-design neural architectures and hardware at the same time to achieve optimal performance. And one of the famous approach towards AutoML, designing neural architecture, designing neural network model is using neural architecture search, in short NAS. So it's a method to automatically design neural network architectures. So here is an example of seminal paper proposed in 2017. They used reinforcement learning to train RNN, and this recurrent neural network generates outputs for neural network architecture parameters like filter height, filter width, stride height, stride width, like number of filters. So, and then we had many follow-up researches right now for neural architecture search. As I said earlier, it's very important to neural architecture to aware of hardware constraints. So there is some other subfield of neural architecture search that considers hardware constraints during the search process. Not only just like neural network accuracy and downstream performance, it also considers like hardware constraints like latency or energy consumption, in searching neural architecture, and they found optimal neural architecture that is good for both both algorithmical way and hardware way. So it aims to optimize models for specific hardware platforms. And there is another streams of works that design not only the neural architecture but also accelerator at the same time. There's no standard terminology, but I would say a neural architecture or accelerator search. So basically, what we do here is that we add hardware design parameters in the search space. So, like for example, like number of processing elements, like size of SRAMs, bandwidth of memory. Those kind of hardware design parameters are included in search space. So and we search through those combined search space to get both optimal network architecture and hardware accelerator design. So as a first part of our research achievement, we proposed something called template-based neural architecture search, accelerator search. So basically what we did is finding out neural architecture and accelerator at the same time. But we found that the problem is the existing co-design approaches have a huge search space. For example, it has to include search parameters for neural architectures like operation type, number of channels, number of layers, convolution size, trace size, and etc. There will be a huge search space just only for this neural architecture search. But also we have search parameters for accelerator architecture, like as I previously said, like a number of PEs, shape of PEs, like buffer size and bandwidth, like that. So since we have this huge search space, in order to search an optimal design point, it will consume a large amount of time and energy. So it's becoming infeasible to find those optimal design points. And also, the second problem in the previous approach is that they calculate hardware cost using like performance model online. So, for example, they measured real performance. Instead of measuring real hardware performance, they like used a performance model for hardware and implemented in the performance estimation stage of accelerator design, accelerator search space, and use the model for final estimation. That leads to inaccurate estimation as well as suboptimal design. So our key idea here is that we use something called template. Here we define a template as an operator and hardware pair. So for example, we have a 3x3 convolution here, and for corresponding this operator, we have this adder tree based hardware architecture. So we paired this operator and hardware together into a single template, and instead of searching for operator and hardware separately, we just search for templates. So by using a template, we can shrink down the search space, and we can calculate the real hardware measurement results offline using hardware block. So since the hardware block is fixed for a certain operator, we can measure the performance, hardware performance of this operator, and we can precisely estimate the hardware performance. So the key is to how to uh, build efficient hardware block. What we did is just we designed the corresponding hardware block for each operator to maximize the utilization. Right? For example, if we have a hardware block for convolution, 3x3 convolution, we have nine um, multipliers, and they are added together to get a single partial sum. And if we have a 5x5 convolution as an operator, we build like 25 multipliers followed by a large adder tree to get a single partial sum. And since the number of multipliers and the size of kernel matches, we always get 100% utilization in this hardware configuration. So we use the dedicated adder tree for convolution operation. And we perform the cell-based search to reduce the search cost. This is something that previous done, not in my work previously. Instead of searching for entire layers, we search for optimal cell, and then we stack the search cell multiple times to complete the neural architecture. And once we find the cell, we will have a corresponding hardware block because they are paired with a template. So we can reuse the template over the layers. And this cell search is conducted by solving the bi-level optimization problem using gradient descent, as previous work Darsh did. So this is the experimental setup for our evaluating our approach. We use the data sets for CFAR10, and we hand-coded RTL for hardware blocks for convolutional layers and other kinds of layers like average pooling or max pooling, and synthesize those hardware codes using Synopsys Design Compiler. And we used the post-synthesis simulation result to measure the accurate hardware latency. So all neural network models are implemented on PyTorch and trained on a single GPU. And this is the list of operators in our search space. We have no operation, skip connect, average pooling, max pooling, different size of convolutions, and depth size convolutions as supporting operators. And using these operators, we make a cell, and we were able to make a corresponding hardware block for those operators and successfully generate the final accelerator architecture. And this shows the experimental result, the comparison result with two previous research papers. So our approach achieved more accuracy, higher accuracy, and lower latency because of two things. First, we have a reduced search space. So this reduced search space helped to efficiently find the optimal point. So that gave us a higher accuracy. And previous approaches suffer from low utilization, such as in previous work, DANCE. They have like monolithic systolic array architecture, and they have rigid shape parameters. So in case of having different wide range of convolution size, they have like underutilization in their hardware accelerators. But our adder tree based architecture is 100%, maintains 100% utilization, and that gave us improved latency. now I'm going to move on to second part of our research. So here we are going to put neural architecture as an input, and we are going to generate accelerator as an output. It's end-to-end accelerator generation, fully automated generation process. The motivation behind this research is that we have a rapidly evolving landscape of neural architectures. So like we have large language models, we have different kinds of convolutional neural networks, we have like many different variants of transformers. Neural architectures are changing very fast, but hardware is not capable of accelerating all these kind of things efficiently. Well, we have GPUs, but GPUs are not the optimal solution in terms of energy efficiency. So we need a dedicated hardware for each neural net. We think that we need a dedicated hardware for each neural architecture. So, but it's quite difficult, right? It's difficult to develop hardware capable of accelerating these networks to facilitate their real-world adoption. So we try to develop a hardware accelerator tailored to a specific neural network on an FPGA. So with this FPGA, we can build any kind of hardware architecture. We can switch the circuit to tailor this circuit to specific neural network. This kind of process is done by human and very high expert engineers and requires a complex engineering process. Challenges for this kind of approach is that we had a neural architecture accelerator search in the previous first part of the research, but they all relies on predefined hardware template. Not only just the previous approach, but also our works also used a predefined hardware template. We have limited hardware design parameters in this accelerator design, and it results in rigid and suboptimal hardware architecture. So our idea was to utilize graph neural networks to automatically develop FPGA-based accelerators optimized for a specific deep neural network. So in this framework, we have two types of neural networks. First one is encoder. It's a graph neural network, and which takes a neural architecture as an input. And this neural architecture is represented using a graph. So node is a tensor, and the edge is an operator. And by taking this graph, and the encoder converts this graph, neural architecture graph, into a latent vector. So we make a representation for this neural architecture, and then we use the decoder to take a latent vector and convert it into a hardware block. Again, hardware architecture can be represented using graph. So the node can be like a hardware block, and edge is a connection between them. So we built this kind of framework to automate hardware generation from the neural architecture in an end-to-end way. So in the encoder, it embeds input neural architecture represented as a directed acyclic graph into a fixed length latent vector. So again, node is a tensor and edge is an operator like 3x3 convolution. So we use the 3-layer graph convolution network for encoder to convert this neural architecture into a latent vector. And then this is the details about decoder. This decoder takes the latent vector and builds a hardware architecture optimal for specific target FPGA hardware. Again, hardware architecture can be depicted as a directed cyclic graph. In this case, node is a circuit element like DSP, adder, multiplier, buffer, register, and etc. And edge is a connection between these circuit elements. In this case, we use graph RNN for decoder to generate this hardware architecture graph. And we train this encoder and decoder in an end-to-end supervised learning way. So we built a custom training data set. We first sampled 1,000 neural architectures from NASBench 201. And we made a corresponding hardware graphs as labels. This required a huge engineering, tedious engineering process, but we hand-labeled all these hardware architecture inputs. And these are restore operators supported in this framework. We have a no operation, skip connection, and average pooling, and 1x1 convolution, 3x3 convolution. This is the experimental setup. We have trained the encoder and decoder using 4 GPUs and sampled different 100 neural architectures from NASBench 201 for tests. We hand-coded the corresponding hardware architecture and programmed on an FPGA. And we use FPGA Xilinx Zinc 1 in our experiment. And the first one shows the hardware generation results. This is an example of a successful generation of hardware from the neural architecture. So at the left side, we have a neural architecture. We have like skip connection, 1x1 convolution, and average pooling. And correspondingly, we have hardware architecture at the right side. This hardware architecture, we confirmed that this hardware architecture is functionally correct with minimum resource overhead. And we compare this result quantitatively with the previous neural architecture accelerator search works. Again, EDD and dense. We normalize the throughput and resource consumptions. Our approach achieved more throughput while consuming slightly less resources, LUTs in FPGAs, because we have a higher flexibility in constructing hardware architectures. Okay, that concludes my talk. We have leveraged AutoML for co-designing neural architectures and hardware to achieve optimal performance. So in the first part, we introduced a concept of template, which is made of operator and accelerator pair, and use this template as a search space to accelerate search process at the same time get optimal design point. This is a hardware-software co-design case. And in the second part, we have a neural architecture as an input, and we flexibly generated output accelerator. It's an end-to-end, fully automated hardware design. In this case, we used a graph neural network encoder and decoder. Encoder takes neural architecture as an input and make a latent vector, and decoder takes a latent vector as an input and generate accelerator. So we showcase the significant improvements in efficiency and performance, paving the way for future self-evolving intelligence and hardware. Our future work includes applying these kind of methods to larger and more complex models. That's all my talk. Any question?
Thank you, Professor Jaehyeong Sim, for your great talk. If you have any question, please raise your hand. We will deliver the microphone. Any questions? Okay, maybe let me give one question. So in part one, if I understand correctly, you are mainly focused on convolutional neural networks, right?
Right.
So I just wonder, your method is also applicable transformer? And in general, I wonder the people in this field, I mean, neural architecture search and architecture accelerator search, in this field, the people also consider, I just wonder, people consider transformer and language model.
Okay. So of course, it is applicable to transformers. Well, we have a few parameters to tune about transformers compared to convolutional neural network. In convolutional neural network, we have like filter size, like we have different channels, we have different kinds of convolutions, we have multiple number of choices to design. But in transformer, we don't have much design parameters. And the second thing is that one of the research shows that the shape of transformer architecture doesn't really matter. Instead, the size of transformer architecture matters in accuracy. So building more transformer architecture is more important rather than like designing more choosing more optimal like head size or like I don't know, different kinds of attention variants.
Okay. Thank you. Any other questions? Okay, then thank you, Professor Jaehyeong Sim, for your great talk again.